All right, continuing on with section 2. So now that we have a good understanding of some terms that we're going to be using in this topic, we're now going to move on to an introduction to thermodynamics. Now, thermodynamics is a very, very, very big field of study. In fact, there's whole courses that are written on thermodynamics. So we are not going to cover all of thermodynamics, but we're only going to cover a very small part of it, which is the thermochemistry part. But what is thermodynamics? Thermodynamics is very simply the study of heat and its transformations into other types of energies. We will provide an example of that later. But thermodynamics essentially just looks and studies how energy transfers from one type to another. Think of energy like money, okay? Money is money, but it can take very different forms. It could be literally cash. It could be money in your checking account, your savings account. Money could be in the form of retirement. So the accounts that it's in may differ, but money is money. In the same way, energy is energy, but the accounts that it's in, such as thermal energy, chemical energy, sound, all the different types of energies that it gets converted to, that is the study of thermodynamics. And so thermochemistry, which we're talking about in this topic, is just a part of that. One thing to keep in mind when we're looking at thermodynamics, or thermochemistry more specifically, is that we don't care how something was achieved. We only care what the initial and what the final is. Okay, so that's known as a state function. So the state of the system is what we're looking at. So once again, we don't care how it was achieved. We only care what was the initial and what was the final condition of the state. And it depends on what we're looking at. So for example, what was the initial volume versus what was the final volume? What was the initial temperature versus what was the final temperature? What was the initial pressure versus what was the final pressure? And more importantly in this topic, what was the initial energy and what was the final energy? And the thing is, we don't care more so what those values are. We only care about the change. We only care about so that's the delta symbol. We only care about the change in the initial to the final. Because you're going to see that we can't actually a lot of times measure what the initial and the final are. We can only change, or we can only measure what the difference is. Okay, that's a little unclear right now. We'll look into some examples in just a moment. Okay, so we're not going to talk too much about thermodynamics, but we are going to talk about some of it. And the first law of thermodynamics, sorry, I had an alarm go off. The first law of thermodynamics does apply to us in this topic. And so it's also known as the law of conservation of energy, which you might have guessed based on the law of conservation of matter, that it states that energy is not created or destroyed, it just gets transferred from one type to another, or from one account to another. And so as an example, let's say you had, I'm going to try to draw, oh God help us all, okay, I'm drawing it really fast, all right, but let's say you had a little toy car, okay, right, and this toy car runs on batteries. All right, so let's say you've got these batteries, and you're going to put them in the car. Okay, so these batteries contain chemical energy, right? The components in that battery stores potential energy, specifically it's known as chemical energy, that has the power to potentially run that car, right? So the chemical energy is in the batteries. So you put the batteries in the car, and all of a sudden you turn the car on, right? And so now that chemical energy is getting converted into mechanical energy. Why? Because the batteries, or the chemical energy, is now turning the gears, right? The gears are turning inside of the mechanism of the car, and so that is turning into mechanical energy. Well, what do those gears do? What are they eventually doing? Well, they're going to make the car start to move. Not only move, its position, but the wheels are going to turn. There's going to be a lot of movement, right? So that gets turned into kinetic energy. And that kinetic energy eventually turns into thermal energy. Why would it turn into thermal energy? Well, as the car goes, it's going to experience friction, not only between the ground, but also all the moving parts inside develop friction. As the batteries die, so dies this whole process down here. But analyzing how those energies are changing from one type to another, that is the essence of thermodynamics. That's what we do. We look at how the energy is changing. And as a reminder, we only care about the change in energy. We just want to know, hey, in this process, what was the energy lost or what was the energy gained in that? Okay? And so we don't care about how it was achieved. We just want to know what the change was. Okay? As an example of that, let me give you a real life example or an analogy. Okay, I may say, you know, let's take a look at your spending habits in a day. I don't care necessarily what your initial bank statement is. I don't care what your final bank statement is per se. I just want to know what was the change in your money throughout the day. Did you gain money or did you lose money? Let's say, you know, okay, you lost, okay, in one day you lost $500. Maybe because you paid some bills, maybe because you filled up on gas, you went to the grocery store, whatever it is, okay, you lost $500. I don't need to know what your bank statement is before. I don't need to know what it was after. I just want to know what the change was. That is essentially what we're looking at in this topic. We're just looking at the change. Only we're not going to look at money. We're going to look at energy. Okay, so in the rest of this video, we are going to talk about internal energy, and we're going to talk about how to calculate it, okay? So internal energy has... Actually, I've seen it two ways. Some textbooks have internal energy as U. I have seen other textbooks have it as a capital E. We're going to go with U because I believe that's what lines up with your textbook. But if it doesn't, if it's capital E, it's the same thing. But internal energy, everything has internal energy. Okay, systems, whatever they are, have a certain amount of internal energy. And that internal energy is composed of those two energies we talked about, kinetic and potential. So those two energies together is what gives something its internal energy. Why would something have internal energy, or why would something have kinetic energy? Well, because, like for example, the table that I'm sitting at, the molecules in that table are moving. They're moving relatively slow, but they're still moving, so they have kinetic energy. But the molecules, my table also has potential energy because of the way the molecules are arranged. So those two things together is what gives my table internal energy. And everything, like I said, everything has internal energy. Now here's the thing. We can't measure internal energy. Like, we can't do it. I can't measure the internal energy of this table. There's too many unknowns, mathematically speaking. But what I can do is I can measure the change in internal energy when it goes through a process, when the table goes through a process. So as a result of a process, we can calculate not the internal energy, but the change in internal energy. And that's where we get the delta U. So here's our very first equation. Delta U is equal to Q plus W. Well, we are familiar with Q. We saw it in section 1. Q is your heat, right? And so Q is going to be measuring, okay, is the system absorbing energy or is it releasing energy? But W is a term referred to as work. And that might be a term that you're not familiar with if you've never seen it before. If you've taken physics before, you might have seen work. But if you haven't, you may not have ever heard what this term is. So let's talk about it. All right. So here's our equation again. We can calculate change in internal energy by just doing simply Q plus W. Very easy equation, right? Just take two numbers, add them together. But here's the trick. You need to make sure that the Q and the W have the correct signs, either positive or negative. So let's talk about that. Reminder, Q is heat, okay? This one's usually easy for students. If the system is absorbing thermal energy, remember, that's known as an endothermic reaction, okay? Endothermic. And that means the value of heat is going to be positive because the system is gaining that energy. But if the system is releasing heat, that's the exothermic process, Q, or heat, is going to be negative because it's getting rid of that energy, right? It's releasing it. So that one's easy for students. It's the work that can be a little difficult, okay? So first I need to tell you what work is. Work is simply applying a force over a distance. Okay, it's applying a force over a distance. In other words, a force is a push or a pull. Okay, so if I push something over a distance, in other words, I make it move, then I can say I've done work on it. So for example, okay, you can't see it. Okay, got my phone here. Okay, all right. So I just moved my phone, right? Ooh, I've got text. Okay, I'm so popular, right? I pushed my phone and it went over a certain distance. So I can say that I applied work. Okay, but let me show you that again. Okay, what if, okay, I am pushing a little bit on my phone, but my phone's not moving because I'm not pushing enough to overcome friction, right? So I am putting a force on the phone, but it's not moving. So am I doing work on the phone? No, because it has to move. Once it moves, then I can say I've done work. Okay, so I always tell students, okay, like I'm pushing against the wall, but it's not moving. It feels like I'm doing work, but I'm not. Okay, I'm not actually moving anything. Okay, so that's what work is. Now, how do you know what sign it is? Okay, if the system is doing the work, okay, if the system, I'm going to write that off to the side, if the system does work, the sign of work is going to be negative. Okay, because I always like to tell students, like, think about, like, okay, I know this image is really small, but think about, like, you're in here, and that's a little creepy, okay, and you are in here, and you're pushing that piston up, right? That piston, you're the system, you're in there, you are pushing up, you're doing the work. Well, if you're doing the work, you're going to feel a little exhausted, right? You're like, whew, I lost energy doing that, right? You lost energy. You are the system, you lost energy. So think about that negative. But if the surroundings do the work, okay, the system doesn't do the work, the surroundings do the work. So for example, in this picture, it's the surroundings that's pushing the piston down. The system's not doing anything. It's the surroundings that's pushing down. In that case, the system has gained energy. Okay, it didn't do anything, it gained energy. So that's going to be positive. That might be a little weird for you. Let's do some practice problems. This right here is just a simple image of what I just explained. So first of all, with heat, which is Q, if your heat is added to the system, remember that's endothermic, Q is going to be positive. If heat is given off, which is exothermic, Q is going to be negative. All right, and then if work is done on the system, work is positive, but if work is done by the system, that's going to be negative. So you can come back to this slide if you need to. All right, we got a few minutes left, so let's do some practice problems 2 and 3. Calculate the overall change in internal energy, delta U, for a system that absorbs 188 joules of heat and does 141 joules of work on its surroundings. So delta U is equal to Q plus W. All right, so first of all, my Q, my heat. So I read here that the system absorbs 188 joules of heat. It's absorbing that energy. So that's an endothermic process. Q is a positive 188 joules. Plus, now work is next. Work, that's not much better, but you get the point. Okay, let's read this, what's going on here. The work is 141 joules, but what's doing the work? Let's see. Calculate the overall change in internal energy for a system that does 141 joules of work on its surroundings. The system is doing the work. So that means it's going to be negative 141 joules. Now, real quickly, some students make the mistake of thinking, oh, if heat is positive, does that mean work is always negative? No, it's apples and oranges. They could both be positive, they could both be negative. It just so happens in this case, it's one and the other. So I'm going to take 188 joules plus negative 141. Okay, now I'm adding. Remember my sig fig rules for adding? It's lowest decimal places. Well, neither of these numbers have decimal places, they're whole numbers. So that means my answer will have no decimal places. So my answer is 47 joules. This is the amount of energy that the internal energy changed by. That was the change in internal energy. So as a result of the system doing those two things, absorbing the heat and doing the work, as a result of those two, the net change in internal energy is measured to be 47 joules. Overall, it gained energy. What was the initial and the final? We don't know, but that's the overall change in the internal energy. All right, we've got one more example problem, but I'm running out of time, so we're actually going to pick up example 3 in the next video.